This is lesson 8.4, part 2, and as promised, we're going to look at a slightly more difficult curve sketching question, but pretty much the same thing. You're still going to be doing a detailed analysis, so like those 7 steps that we talked about in the previous video, in order to sketch something. But now this something looks a little bit weird, like I don't know what that actually looks like. So let's just start and see what happens. Okay, so we're going to start with our first step, which is finding the first and second derivatives. So here we go. I'm going to probably need those for a little bit later. All right, now we're going to get into analyzing the asymptotes. So looking first of all at the vertical asymptotes, I don't see a denominator under there, so we're not going to have any. However, I'm not super familiar with x squared and e to the power of x multiplied together. They may have like a horizontal or an oblique asymptote. And so the way that I would probably analyze it, and I'll show you this right here, is I would like to see, normally when we look at our horizontal and our oblique asymptotes, we check out what the limit is as your x values approach a very large or very negative large number. Okay, negatively large number. There we go. Okay, so what I'm going to do is I'm going to test those in my f at x function, so my original blue function. Using limits and their properties, I can split up the limit of just the x squared and the e to the power of x. So once I've split them, I can then take the infinity and plug it into my x or into this x. So I get something weird like e to the power of infinity and also infinity squared. So infinity squared is just like a really large number. Oh my god, it's so cute. Do you guys see that? Look, it looks like Batman and Robin like glasses. You know, the little, okay, I'll stop. Anyways, you have a really large number and you're squaring it, which means you're going to have an equally large number. E is like 2.71823, something like that. If you're going to make it to the power of a huge number, you're going to get a huge number because it's an exponential function. So if you take a huge number and you multiply a huge number, you get a green Ninja Turtle. This is so cute. Look at that. Like it's Raphael, see? All right. Oh, that's awesome. Anyways, okay. Going on to the other side, when you have negative infinity and you're plugging it into your x, well, then you're going to have negative infinity in brackets squared, which will give you a positive infinity. But putting this into the negative, putting the negative infinity into your x exponent is going to flip the e upside down. So you're going to get 1 over e, right? Because you're going to flip that with the positive infinity. And so if you plug in infinity now, this entire thing is going to approach 0 because you're going to have a very large number on the bottom. So 1 divided by an extremely large number is going to be 0. So when you multiply 0 with any number, you're still going to get 0. This guy didn't really tell us much other than the fact that we can make Ninja Turtles out of infinity signs and large circles. The right side did tell us something. So as we approach a very large negative number for our x, we actually approach 0 for our y. And so that means that we have some sort of an asymptote. This is going to be a horizontal asymptote, and it's going to be at y equals to 0. Okay, again on the left-hand side, as x approaches positive infinity, I mean, obviously your function is going to go towards something larger and larger. And so we'll see that. In fact, why don't we add that in a second? Let's do our behaviors first, and then we'll add in what we think our function is going to look like. So using a horizontal asymptote of 0, I'm just going to place zeros over here and here. And I'm going to add in a very negative number to test the negative limit, so the negative bound. I chose negative 100 because it is like a very small number, and I put it into f at x, which gives me an extremely small number. However, it is a positive number and it is above 0. So it is 0.0000, many zeros, 37. Okay, so that is above 0, which means it's going to be above our horizontal asymptote. So that's what that says. Putting in a very large x value, we had said that our Ninja Turtle is going to be approaching infinity, positive infinity, right? And as you can see, when we subbed in 100, we get this huge, huge number. And that is obviously above our horizontal asymptote, but it's not approaching it. It's actually approaching infinity. So it's getting into like a really large number realm. So before we continue, let's just start to graph that. All right, so here's my graph. I have my y equals to 0 horizontal asymptote, but no vertical, no oblique asymptotes. So adding in horizontal asymptote right here. Let's make that nice and pink, just to match. There we go. Okay, I'm going to write that down as well through that color. This is y equals to 0. And as we approach positive infinity for the x's, your graph seems to be like, how do I draw this? It seems to be growing, like huge, like really large numbers, exponentially. Okay, as it's approaching negative infinity, so the other end of the graph, it is above your asymptote, but it's skimming. It's getting super close. Okay, so this is what I got so far just on what I did for analyzing the asymptotes. Let's get into the local extrema. So this is our first derivative. Again, there's no denominator, so I'm not going to analyze any of the denominator, but I'm going to set it equal to 0 to find out where the slope is 0, aka what are my max and mins. So this guy can be broken down into compartments, this one, and this one. Where do they all equal to 0? Because wherever that is, those x values are where my max and min are. Okay, so the first one we can't actually solve. E to the power of, well, nothing really will ever give you a 0 because this is an exponential function and it never touches 0. So this guy is out. The next one, x is equal to 0, well, cha-ching, we're done. The third one is going to be just -2 because we're going to bring that over. So we have two critical values that we're now going to put into an increase and decrease chart because I don't know if that's a max or min at 0 and -2. Starting from the smallest to the larger number, we're going to then create our intervals. Okay, and we're going to sub in numbers within those intervals into our first derivative to see if our slope is positive or negative. In the first region, it looks like it's a positive slope, and so notice that your original function is increasing. In the middle, our first derivative, there we go. First derivative is negative, which means we have a negative slope. That means our blue function is decreasing. And in the third region, we have a positive, which means, again, your function is increasing. There should be a max here because it's going from increasing to decreasing, and that is at an x value of 2. I can find that point by subbing the 2 back into the function and getting my local max. Did I put 2? I should have put -2. My bad. Okay, now it looks like it's going this way into a min. So there is a min right there at x equals to 0. And so here is my minimum by subbing 0 back into our original function. Okay, and again, we can always list out what are our intervals of increase and decrease. But now that we have a max and min and we can clearly see what that looks like, why don't we put them on our graph? Okay, so I have them right here and right there. We'll add those in. So that's kind of weird. We do have, let me see. This guy right here, our minimum at 0, 0, which is on the horizontal asymptote. Like I said before, sometimes you will cross a horizontal asymptote, but what really matters is where your graph is at the ends of those asymptotes. Like the end behavior is much more important than the middle of the graph. Okay, so it's okay if it does cross. -2 and 0.54, -2, 0.54, maybe somewhere here. All right. So I don't know that I want to commit to drawing the rest of the graph yet. I think I might want to find some more information. That means I'm going to do my second derivative now. This is our fourth step, and that's going to give me my point of inflection. So setting it equal to 0, because again, I want to know where, I guess, the concavity and points of inflection are, what the behavior is going to be like, and so on. So setting it equal to 0 allows me to solve for my critical numbers. So this one we had said already is not possible. Solving the other one, setting it equal to 0, you're going to probably have to use quadratic formula, because I can't really think of anything that multiplies to 2 but adds to 4. So using the quadratic formula, you will get an exact answer of this or your approximated answers. So those are the two critical numbers that will give you your points of inflection. We're going to use those in our chart to figure out what our concavity looks like. Okay, so start off with the leftmost one and then go towards the rightmost one and set up your regions of domain. Okay, subbing in numbers within those domains, you're going to put those into your second derivative to tell us, well, what is the concavity? Is it a positive concavity or a negative? So is it concave up or concave down? So for example, like the second one is going to be a negative, and so you're going to get a concave down, which is like an unhappy face. All right, now in between, you'll see that you'll have your point of inflection right here at your x value, and so we can sub that number into our f at x to find our first point of inflection, and subbing this into our f at x again, we can then get our second point of inflection. Recall that like the point of inflection basically means that right here and then right here, you're going to have some sort of a graph that goes up and then, down and then up and so on. Then you'll have your second point of inflection, which is right here, because then this guy's going to go back down again. Okay, so you can, like they might not look like U's like that, like so curvy, but they do have the general shape of like increasing and decreasing slopes. So here we go, just listing off our increase and decrease, and let's put those points of concavity, not points of concavity, that doesn't even make sense, points of inflection into our graph. So here are those POIs. Okay, so negative 3.41 and 0.38 might be somewhere here. Okay, and then the other one, negative 0.59 and 0. Something like somewhere around there, I guess, would be the second one. I think I might want like a tiny bit more, and so I would do x and y intercepts. So x and y intercepts solving when your x is equal to 0 and when your y is equal to 0. I get the same points that I think I already had. I had 0, 0 already. That was one of my minimums. But that's okay. We just want to check to make sure. Any extra piece of information is a good piece of information. Okay, so this one's done as well. And now let's draw the graph. It does look like, okay, so we had said concave up, concave down. That's a max, going concave down to concave up. That's a min. Ta-da! Okay, maybe like a little bit wonky on one side. I don't want that to look like a max. So maybe something like that. All right. So once we have our function, you can then say a little bit more about the domain and the range. And obviously on a graph, I would expect your x and y to be on the graph. Actually, I didn't do this on the last video, so I definitely should show you this on this video. You want to label your x and y for all communication marks. Arrows at the ends of your function. Okay. Labeling your asymptote. Having your scale go all the way to the ends, and don't be lazy. And then also what I didn't put on my last graph, which I probably should have, is the equation itself. So make sure that you guys have y equals to your, what was it, x squared times e to the power of x or something like that. So label your graphs with all of those and you will definitely have all of those communication marks checked off. Guys, that was like unit 8. We're done. We have one more unit, then we're done the course. This is so crazy. We have maybe 4 more videos coming, and then I get to relax. Okay, I will see you later. Have a great day.